Welcome to the video solution of your selected question from the Mathematics the Easy Way DVD. If you have not yet seen the introduction video on the DVD, please do so now, as it outlines how the Easy Way series will help students to be successful in their CXC exam. While the Easy Way video solutions will help to cement the understanding of certain special questions, the solution books are still absolutely necessary as they cover all the various types of questions that are set in CXC exams.
We are now at our last question, question 11, and we are doing part A, a vectors question. Now, this question gave us this vector diagram and tells us of position vectors OA and OB. So it's a diagram showing position vectors OA and OB. So what we want to do firstly is put down the coordinates of A and B as shown on the diagram here. Now the point A has coordinates -1, 3 and B has coordinates 5, 1. So let's go ahead and show those coordinates. So that's it. A is the point -1, 3 and B is the point 5, 1. Let's now go to the questions. The first question is asking us for the vector OA. Now that's a position vector of A. And position vector of A is the displacement from the origin to A. So to go to A from the origin, we would have to go 1 unit backwards and 3 units upwards. And so the column matrix for the vector OA, which is the position vector of A, is -1, 3, having the same values as the coordinates of the point A. So that's the vector OA, the position vector of A, -1, 3. And then the second question is asking us for vector OB, that's a position vector of B. And to go from O to B, we go 5 units to the right and 1 unit up. So those are the components of vector OB. 5 units in the X direction, 1 unit in the Y direction, and the position vector of B would have the same values as the coordinates of B. So let's show that position vector. So that's a column matrix for the position vector of B. 5, 1. Vector OB is 5, 1. Then the third part is asking us for the vector BA. Now that's a displacement vector. The displacement vector that will take us from B to A. And if you look at the diagram, to go from B to A, going along the components of the X and Y, we would have to go 6 units backwards, 1, 2, 3, 4, 5, 6, and 2 units upwards, 1, 2. So therefore, the vector BA, based on the diagram, would be -6, 2. -6 in the X direction, 2 units in the Y direction. But we can also calculate the displacement vector BA using the position vectors OA and OB. And the displacement vector BA is given by the position vector of A minus the position vector of B. That's O times the last minus O times the first. A is the last and B is the first, and so the vector BA is OA minus OB. The position vector of the last, which is A, so that's OA, minus the position vector of the first, which is B, so that's OB. Vector BA is OA minus OB. So we can use these to calculate the vector BA, and this is it. Vector BA is column matrix for OA, that's -1, 3 from here, minus the column matrix for OB, that's 5, 1. And when we do that calculation, we see -1 minus 5 is -6, and 3 minus 1 is 2. So the displacement vector BA is -6, 2. And that corresponds to the displacement that will be required on the diagram to go from B to A. 6 units backwards and 2 units upwards. So that's the answer for part 1 of question 11A. Let's move down now to part 2. Now part 2 tells us that G is the midpoint of AB. G is the midpoint of this line AB. So G will be located halfway the distance from A to B. So that's right here. So we can go ahead and put that point G on the diagram. So that's the point G. And we have from the first part that the position vector of A is -1, 3, position vector of B is 5, 1, and the displacement vector B is -6, 2. And the first thing we're required to find in this section is the vector BG. Now the vector BG, based on this diagram, is the vector that will take us from B to G. That's right here. And clearly that vector BG is simply half of vector BA. So we can show that right here. Vector BG is half of vector BA. And so we can show that calculation BG is half of -6, 2, which works out to be -3, 1. And this diagram confirms that the displacement from B to G is -3, 1. Going from B to G along the components, we would have to go 3 units backwards, 1, 2, 3, and 1 unit up. That's it. To go from B to G, 3 units backwards, 1 unit up. So that confirms this calculation. The displacement vector BG is -3, 1. So that's the answer for that part. And then we're required to find the vector OG. Now the vector OG is a position vector of G, and that is the vector that will take us from the origin to the point G, the vector straight here. But the components for that vector would be 2 in the x direction and 2 units upwards. G clearly is located at the point 2, 2, so the vector OG will be 2, 2. But we can also calculate the position vector of G using the vector midpoint formula for the position vector of the midpoint of a line. Since G is the midpoint of AB, then the vector OG is given by half the sum of the position vectors of the endpoint of the line AB. So that's half the position vector of A plus the position vector of B. That's the midpoint formula for the position vector of the midpoint of a line. So all we need to do is substitute the matrix for OA and the matrix for OB here, and that will give us the position vector of G, which is OG. So that's it. Half OA is -1, 3 from here, and OB is 5, 1 from here. So when we do this calculation, -1 plus 5 is 4, and 3 plus 1 is 4. We end up with half of 4, 4, and half of 4, 4. The result is 2, 2, which confirms what's on our diagram. The vector OG is 2, 2, and that's the answer for that part of the question. Now let's move down to question 11b. Now question 11b gives us two matrices, L and M, and these are our two matrices. L is 3, 2, 1, 4, and M is a 2 by 2 matrix, -1, 3, 0, 2. The first question is asking us to evaluate L plus 2M. That's the matrix L plus 2 times the matrix M. So let's show that calculation. So that's L plus 2 times the matrix M. And 2 times this matrix means we multiply each element in this matrix by the 2. So let's show that calculation here. So this is the matrix from here, and then this 2 times M becomes 2 times -1 is -2, 2 times 3 is 6, 2 times 0 is 0, and 2 times 2 is 4. So all we need to do now is add these two matrices, and when you add matrices, you add the corresponding elements. So the result of this addition is this: 1, 8, 1, 8, because 3 minus 2 is 1, 2 plus 6 is 8, 1 plus 0 is 1 here, and 4 plus 4 is 8. So that's the result. L plus 2M is the matrix 1, 8, 1, 8. So let's move to part 2. Now part 2 is asking us to evaluate LM. Now LM is equal to the matrix L multiplied by the matrix M. So what we have is a product of two 2 by 2 matrices, and the result is going to be a 2 by 2 matrix. So let's go through the process of carrying out this multiplication. So the result is going to be a 2 by 2 matrix, which we will conclude here. And I've inserted codes here to demonstrate how the matrices multiplication is done. Now R1 C1 here means row 1 column 1. The element here is in the first row and the first column. So what it means is we have to multiply the first row of this matrix by the first column of this matrix. When we do our multiplication in matrices, we take the rows from the first matrix and the columns from the second matrix. And so this element, which is in the first row and the first column, means we have to multiply this first row by this first column. So let's go ahead and show that multiplication. So that's it. We are multiplying the row 3, 2 with the column negative 1, 0. That's what we have here. And how we multiply matrices is along the row and down the column. So we'll multiply this 3 by this negative 1 and this 2 by this 0 and do the addition. So let's show the calculation here. So that is it. 3 multiplied by negative 1 plus 2 multiplied by 0. And the result of this, 3 times negative 1 is negative 3 and 2 times 0 is 0. So the result of this addition is negative 3. So we can show that result here. And then this element is in the first row and the second column. Hence we have R1 C2. First row, second column. So let's show those two matrices. So I'm multiplying row 3, 2 by column 3, 2. And so we'll multiply 3 by 3 and 2 by 2. And let's show that calculation here. So it's 3 times 3 plus 2 times 2. So that's 9 plus 4. And so the result here is 13. Okay? And then this element is in the second row and the first column. Row 2, column 1. So it means we multiply this second row by this first column. So let's show the matrices here. So we are multiplying 1, 4 here with negative 1, 0 here. And so we'll multiply this one by this negative 1 and this 4 by this 0. And we'll do that calculation right here. So it's 1 multiplied by negative 1, that's negative 1, and 4 multiplied by 0 is 0. So the result of this calculation is negative 1. And so this element here is negative 1. And then this final element is in row 2, column 2. So we multiply row 2 by column 2. So let's show the matrices here. Row 2 by column 2, and that's it. Row 2 is 1, 4, and column 2 is 3, 2. So we're doing this multiplication here. So it's 1 multiplied by 3 and 4 multiplied by 2. So let's show that 1 multiplied by 3 plus 4 multiplied by 2. And when we do this calculation, that's 3 plus 8. The result here is 11. And so the multiple of the two matrices, L multiplied by M, the result is negative 313, negative 111. And that's the answer for question 11B, part 2. Let's move down now to question 11C. Now question 11C gave us the matrix Q 4211. And first, we're required to calculate Q to the minus 1. Now that's the inverse of the matrix Q. And the inverse of the matrix Q is given by 1 divided by the determinant of the matrix Q multiplied by the adjoint matrix of Q. That's what this means. Q superscript D here means the adjoint matrix of the matrix Q. That is Q to the minus 1 equals 1 divided by the determinant of matrix Q multiplied by the adjoint matrix of Q. And we can show how the determinant of Q is calculated and how the adjoint matrix of Q is determined. And this is it. The determinant of Q is obtained by multiplying the product across here in the matrix Q minus the product across here. So the product of these two elements minus the product of these two elements. That's how we calculate the determinant of Q. So it's 4 multiplied by 1, 4 multiplied by 1 minus 2 multiplied by 1, 2 multiplied by 1. That's this product minus this product. So that's the determinant of Q. And then the adjoint matrix of Q, which is here, is obtained by interchanging these two elements. These are the main diagonal elements. So we interchange the main diagonal elements such that the 4 goes here and the 1 goes here. And that's what we have, an interchange of the main diagonal elements here. And then these other two elements, we change the sign. So this 2 becomes negative 2 and this 1 becomes negative 1. So that's how the adjoint matrix is constructed. Interchange the main diagonal elements. So 4, 1 across here becomes 1, 4. And then we change the sign of these other two elements. So this 2 becomes negative 2 and this 1 becomes negative 1. And then all we need to do is simplify this calculation. So this reduces to 4 minus 2 is 2 here. And so we have a half multiplied by this matrix. And so to multiply this half by this matrix, we multiply each element in the matrix by half. And the result of that multiplication is that Q to the minus 1 becomes 0.5, negative 1, negative 0.5, and 2. That's because a half multiplied by 1 is 0.5. A half multiplied by negative 2 is negative 1. A half multiplied by negative 1 here is negative 0.5. And a half of 4 is 2. And that's the result for Q to the minus 1, the inverse of the matrix Q. So that's part 1 of question 11C. Let's move down now to part 2. Now what we have so far from part 1 is the matrix Q equals 4, 2, 1, 1, and we calculated Q to the minus 1, that's the inverse of the matrix Q, 0.5, negative 1, negative 0.5, 2. And we are asked now to calculate the values X and Y which satisfy this matrices equation. Now if we observe, this 4, 2, 1, 1 really is the matrix Q. So we can actually go ahead and show that. So in reality, what we have is a matrix Q multiplied by this column matrix XY being equal to this column matrix A3. And by simple matrices transposition from this matrices equation, if we multiply both sides by the inverse of Q, the result is that the matrix XY from here becomes equal to the inverse of the matrix Q multiplied by this matrix A3. So that's a straightforward transposition of this matrix. Theoretically, what happens is that both sides of this matrices equation are multiplied by the inverse of this matrix Q. Right? Both sides are multiplied by Q to the minus 1, and then Q to the minus 1 multiplied by Q gives us the identity matrix, and so the result on this side is the matrix XY. And so all we need to do to calculate this matrix XY is to substitute the inverse matrix of Q, that's Q to the minus 1 from here in this position, and then carry out the calculation. So let's show that. So the matrix XY is the inverse of Q, that's Q to the minus 1 from here, multiplied by A3. And the result of this multiplication is going to be a column matrix. and we can go ahead and show how this calculation will be done. Again, this element here, the element for here, which is represented by this code, is row 1, column 1. So we are multiplying row 1 here by column 1 here to get this element. So it's 0.5 multiplied by 8 and negative 1 multiplied by 3. So let's show that calculation. That's it. 0.5 multiplied by 8, 0.5 multiplied by 8, and then negative 1 multiplied by 3, negative 1 multiplied by 3. And the result of this is 4 minus 3. So the result here is 1. So that element is 1. X is therefore 1. And then this element here is row 2, column 1. So we multiply this row 2 by this column 1. So we are multiplying this negative 0.5 by this 8, and we are multiplying 2 by 3. We go along the row and down the column. So it's this element multiplied by this element, and this element multiplied by this element. Row 2 multiplied by column 1. So let's show that calculation here. And that's it. Negative 0.5 multiplied by 8 plus 2 multiplied by 3. This is negative 4 and this is 6. So negative 4 plus 6 is 2. So the result here is 2. And so the matrix XY here, the column matrix XY is 1, 2. And therefore X is equal to 1 and Y is equal to 2. And we can show that solution line. The solution is X equals 1, Y equals 2. And that's the answer for this question 11C part 2. And that's the end of this production of the January 2012 exam video solutions. We will look to do more video solutions for other exam papers in the future, and I hope you learned a lot, and we'll continue to do our best to help students pass their exams, their mathematics exams, the easy way. Okay, bye.
You have just seen the video solution for a special CXC question, but this is only one of the many different ways that these questions are written. All mathematical principles can only be fully understood by solving many questions, and so I always tell my students, more maths equals better maths, and if they study hard, they will pass easily. All the various types of CXC questions are covered in the Easy Way Mathematics Solution book, and you need to practice every single one of them. Other books in the series are the Easy Way Multiple Choice Specimen book, the Easy Way Unit 1 Cape Mathematics Solution book, and the Easy Way Account Solution book. Please feel free to contact me with your comments and queries at any time.